This is Lesson 3, Applications of Dot Product. This is from the Grade 12 Calculus and Vectors course, from the 5th unit, Cartesian Vectors. So in the previous lesson, we learned about the formula for dot product, and in this lesson, we're going to use our understanding of dot product to solve questions involving projections of vectors, calculating work, and calculating angles between two vectors. So we'll use our understanding of everything from Lesson 2 to solve problems involving those three things. So once you're ready to begin, head on over to jensenmath.ca, go into the Calculus and Vectors course, go to the 5th unit, which is the second vectors unit, and we are on the 3rd lesson. Here on this page, you can get a blank copy of the student lesson that you can fill out as we go along, and then after the lesson is over, I would encourage you to try the practice problems on the worksheet, and after you try your practice problems, you can check your solutions by clicking on Worksheet Solutions. So let's get started. Let's start with a warm-up question, and I only call this warm-up because we did a mechanical work question in the previous lesson, so this is somewhat of a review. But this is still an application of dot product. The example says a desk is pushed with a force of 50 newtons at an angle of 45 degrees below the horizontal. If the desk is pushed 5 meters, how much work is done? So this is actually a dot product question. When we're asked to calculate a mechanical work, as a reminder here, is the product of the magnitude of the displacement traveled by an object with the magnitude of the force applied in the direction of motion. So that's exactly what dot product is. Dot product is the product of the magnitude of one vector with the magnitude of the other vector that's applied in the direction of the first vector. So that's what dot product is. That's exactly what mechanical work asks us to do. So let me draw a vector diagram here of this scenario so we can better understand what it's asking. So I started by drawing my desk. This desk has a displacement of 5 meters, and there is a force that is being applied to this desk at an angle of 45 degrees below a horizontal. So let me label these two vectors and indicate what their magnitudes are. So this is my displacement vector, and I know its magnitude is 5 meters. And this is my force vector, and I know its magnitude is 50 newtons. And I know the direction of this vector is 45 degrees below a horizontal. So I'll draw in an imaginary horizontal and label this angle 45 degrees. Now when I'm calculating work, when I'm finding the product of the displacement with the magnitude of the force that is applied in the direction of the displacement, that's dot product, so I have to arrange them tail to tail. So let me start by redrawing this force vector so that it's tail to tail with the displacement vector. And I want you to also notice that the displacement is perfectly horizontal. We're assuming this desk is on a floor and it's being pushed along the floor. So the angle it makes with the displacement when they're tail to tail is also 45 degrees. Now what I'm interested in doing, I'm interested in calculating the mechanical work, and that's the product of the magnitude of the displacement with the magnitude of the force that is applied in the direction of the displacement. So what that formula would look like, work would equal the magnitude of the displacement times the magnitude of the force applied in the direction of the displacement. Well, that's the projection of the force onto the displacement vector. So to write that, I would write the projection of the force vector onto the displacement vector. And we learned about that in the last lesson. So if you don't know about vector projections, make sure you go back and watch lesson 2. And if we want the magnitude of this, oh, and I should also draw that for you. Let me draw what that projection vector would look like. So it would look like there's a few properties. Its tail is going to be at the same place the tails of the force and the displacement vector are. And the tip is going to go to a point so that if I were to connect the tip of this vector to the tip of that vector, it would form a 90-degree angle with the projection vector. And I should also mention that it's always going to be parallel to the vector that you're projecting onto. Since we're projecting onto vector d, the displacement vector, the projection vector is going to be parallel to vector d. So this blue vector is my projection vector. That's my projection of the force onto the displacement. And if we use SOHCAHTOA, we would figure out that an equivalent expression for the magnitude of the projection of the force onto the displacement vector would equal the magnitude of the force times cosine of the angle between them. We get that using SOHCAHTOA. And this is the dot product formula. This is what d dot f is equal to. So we could have just started this question just by writing what we're trying to find is the dot product of D and F. This is just a way of me reminding you the mechanical work is just dot product. So now that we remember it's just dot product, we use the dot product formula and sub in what we know. We know the magnitude of the displacement was 5 meters. We know the magnitude of the force was 50 newtons. And cosine of the angle between them was 45 degrees. And now I can simplify this. 5 times 50 is 250, and cos of 45 is a special angle, so I know that's 1 over root 2, or rationalized, it's root 2 over 2. And if I simplify this, 250 divided by 2 is 125, so I get 125 root 2 as an exact value for the mechanical work. And the units we're working with here are Newton meters. The displacement was in meters, the force was in newtons, so this is in Newton meters, which is equivalent to joules. Let's move on now and look at how we can use a dot product formula to calculate an angle between two vectors. Let's move on to the part where we find the angle between two vectors. So to determine the angle between two vectors, we can rearrange the dot product formula. And that's the dot product formula right there. A dot B equals the magnitude of A times the magnitude of B cos theta. If we rearrange that to isolate cosine theta, we then have a formula which we could use to solve for theta. So how do we isolate cosine theta? Just divide both sides by the magnitude of A times the magnitude of B. Divide this side and this side by the product of those magnitudes. And when we divide both sides by the product of those magnitudes, they cancel out on the right side of the equation, and we're left with cosine theta equals A dot B divided by the magnitude of A times the magnitude of B. So here's our rearranged dot product formula. But when does this formula work? When can we use this formula to solve for the angle? Well, and remember I should mention the angle is always going to be the angle between the vectors when they're placed tail to tail. So when does this formula work? It works when we're able to calculate the dot product of the vectors, and we're also able to calculate their magnitudes. And we'll only be able to do that if we're given the vectors in algebraic form, meaning we're given the x and y components of the vector. So let's see what those questions look like. Example 2 says, determine the angle between each pair of vectors. I have two algebraic vectors, vector g and vector h. And we learned back in lesson 1 what this notation means, where it says vector g equals, then inside square brackets, 5, 1. That means if I were to translate vector g so its tail is at the origin, the tip would be at the point 5, 1. So here's a picture of the graph of that vector that I imported from GeoGebra. Notice tail is at the origin, tip is at the point 5, 1. So vector h, its tail would be at the origin and its tip would be at negative 3, 8. So now that you remember what this notation means, let's find the angle between those vectors. And when we talk about the angle between vectors, we're talking about the angle between them if they were placed tail to tail. So I can use the rearranged dot product formula to find the angle between two algebraic vectors. So cosine of theta would equal the dot product of vector g and h divided by the product of their magnitudes. So the magnitude of vector g times the magnitude of vector h. And now I need to remind you how we can calculate the dot product of algebraic vectors and the magnitudes of algebraic vectors. So I'll do that over to the side here as well. So let me remind you about the formula for the dot product of algebraic vectors. All we have to do is find the product of the x components of the vectors, and then add the product of the y components of the vectors. So back over here, let's calculate the dot product between vector g and h. So cosine theta equals, I just need to multiply the x components, 5 and negative 3, and then add the product of the y components, 1 and 8. And that will give me the dot product, right? Dot product is called the scalar product of vectors because it just results in a scalar value. It's not a vector. Now I need to divide this by the magnitude of both of the vectors multiplied together. So I'm going to have to figure out, well, what's the magnitude of vector g? And looking at this diagram, finding the magnitude of this line would be very easy to find. Because think of this as a right triangle. In this right triangle, this side length is 5, and this side length is 1. Notice this side length is equal to the x component of the vector, and this side length equals the y component of the vector. So I could use Pythagorean theorem to solve for the magnitude of vector g. The magnitude of vector g squared would equal the magnitude of this side squared, which is equal to whatever the x component is. So the x component of vector g squared plus the magnitude of this side squared, and this side is always going to be equal to the y component of the vector. And then I could isolate the magnitude of vector g by square rooting both sides, and I would get the magnitude of vector g equals the square root of the x component squared plus the y component squared. And we came up with this formula back in lesson 1, I just wanted to remind you about it now. So if I want the magnitude of vector g, I just have to do the square root of the x component squared, so 5 squared, plus the y component squared, 1 squared. Now I need to multiply that by the magnitude of vector h. And vector h, its x component was -3, its y component was 8. So I'd have to do the square root of the x component squared, -3 squared, plus the y component squared, 8 squared. So there's everything I need. My only unknown is theta. I now just have to isolate for theta. Let me simplify this ratio first, though. In the numerator, I have -15 plus 8, that's -7. In the denominator, I have root 26 multiplied by root 73. And now I need to isolate theta by doing inverse cosine of this ratio. So theta is about, so I'm just using the Desmos calculator quickly, so inverse cos of -7 over root 26 times root 73, and it's about 99.2 degrees. So theta equals 99.2 degrees. So what we just figured out, if the vectors were placed tail to tail, the angle between them would be 99.2 degrees. Let me just go over to GeoGebra just to make sure you understand what we found. So here in GeoGebra, I have it graphing vector g and vector h. We found out that the angle between those two vectors, this angle inside here, is about 99 degrees. Part B, same question, find the angle between the two vectors. They're algebraic vectors, so we can use the rearranged dot product formula. Cosine theta equals a dot b divided by the magnitude of vector a times the magnitude of vector b. So if I want to do a dot b, I multiply the x components, -3 times 4, plus multiply the y components, 6 times 2. Now I divide by the magnitudes. The magnitude of a, I would do the square root of the sum of the squares of the components. So the square root of -3 squared plus 6 squared. And the magnitude of vector b, I would do the square root of 4 squared plus 2 squared. And this is what cosine of the angle equals. Let me simplify that ratio before I evaluate the angle. So I have -12 plus 12. Well, that's 0. So I have 0 over 9 plus 36, that's root 45. 16 plus 4, that's root 20. So 0 divided by that product is just 0. And for what angle do we get a cosine ratio of 0? The angle is 90. So theta equals 90 degrees. 90 or 270, but we always want the angle between 0 and 180 when we're describing the angle between the two vectors. So therefore, the angle between the two vectors, 90 degrees. And let me just show you those two vectors in GeoGebra to verify. So there we have vector A and vector B, and this sure looks like a 90-degree angle between those two vectors. Let me remind you about a couple properties of dot product and how they could have tipped us off to what our answers were going to be. Dot product is 0 when the vectors are perpendicular to each other, and the dot product is negative when the angle between the two vectors was between 90 and 180. So I knew I would get an answer here that was between 90 and 180. If I had have gotten a positive dot product, I would have known the angle between the two vectors was between 0 and 90. And we learned about all of that in lesson 2. Let's move on to part 2. This is all about applications of vector projections. And before I talk to you about the applications, I need to make sure you remember what a vector projection is. So in this diagram, I have vector A in red, vector B in blue, and this green vector is what I call the projection of vector A onto vector B, and that's what this notation says. So projection vectors follow 3 general properties. If we're projecting A onto B, first of all, A and B have to be placed tail to tail, which they are. The projection of A onto B would have its tail at the same place as the tail of vector A and B. The projection vector will be parallel to vector B, So it'll be parallel to the vector that you're projecting onto. Since we're projecting onto B, the projection vector will be parallel to B, meaning it's either going in the same direction as B or in the opposite direction as B, depending on what this angle here is. And the third property is where the tip of the projection vector goes to. So like I said, it's going to be parallel to B, but the tip stops at a point so that when you connect that point to the tip of the vector you're projecting, so in this case vector A, there is a 90-degree angle with the projection vector. So once again, three properties. Projection vector has its tail at the same place as the tail of A and B. It's parallel to vector B, and when connecting the tip of the projection vector to the tip of vector A, there's a 90-degree angle with the projection vector. And let me just go through a few scenarios with you about how the projection can change depending on what this angle is. So in this diagram, notice the angle is acute. It's between 0 and 90. And when that happens, the projection vector, if we're projecting A onto B, the projection vector is going to be going in the same direction that vector B is going in. If the angle is obtuse, so between 90 and 180, then the projection vector, if we're projecting A onto vector B, the projection vector is actually going to go in the opposite direction of vector B. And if the angle between the vectors when they're placed tail to tail is 90 degrees, then the projection of A onto B is actually the zero vector. Its magnitude is 0. Often we talk about a projection vector as being a shadow that's being cast. If we look back to these examples, if we were to cast a shadow of A onto vector B, it would be that vector right there. So if we try and cast a shadow of vector A onto vector B, there is no shadow cast. So that might be a good way of helping you understand why the magnitude of the projection of A onto B would actually just be 0. And that should hopefully help you understand why earlier when we did dot product and we got 0, we knew the vectors were perpendicular to each other. So this is an important property. The dot product would be 0 for perpendicular vectors. We talked about that in lesson 2. And this is because dot product involves magnitudes of projections. So when the magnitude of a projection equals 0, the dot product becomes 0. And when is the magnitude of the projection 0? When the angle is 90 degrees. This is the most complicated part of the lesson where we're going to come up with 4 formulas. We're going to come up with 2 formulas for geometric vectors and 2 formulas for Cartesian vectors. For each type of vector, we are going to come up with a formula for a vector projection and the magnitude of a vector projection. So magnitude of a vector projection is just the length of the vector projection. And when I say calculate a vector projection, I mean we need its length and its direction. So we're going to do 2 formulas for geometric vectors and for Cartesian vectors when we're trying to find vector projections or the magnitude of those vector projections. So I'm going to walk you through how we're going to come up with those formulas. And bear with me as we try and understand where the formulas come from instead of me just giving them to you and you just accepting them without understanding. Let's try and understand them. So to understand them, we have to first remember what dot product is. So in this diagram, I have vector A and vector B, and I also have the projection of vector A onto vector B as the green vector there. So remember that the dot product between 2 vectors is equal to the product of the magnitude of one vector, I'll choose vector B, times the magnitude of the other vector, vector A, that's going in the direction of vector B. So how do we indicate that? Well, what's the magnitude of vector A that's going in the direction of vector B? That's represented by the projection here. So multiply vector B by the magnitude of the projection of vector A onto vector B. And what we actually want up here, we actually want a formula for the magnitude of the vector projection. So I should mention right now we're going to focus on the geometric vectors first. Right here I have 2 geometric vectors. If I want to figure out a formula for the magnitude of the projection of A onto B, I have to look at this right triangle right here. And looking at that right triangle, notice that cosine from this angle would equal the magnitude of that side over the magnitude of that side. Cosine of theta would equal the magnitude of the projection divided by the magnitude of vector A. And then rearrange this to isolate for the magnitude of the projection of B onto A. And I get the magnitude of the projection equals the magnitude of A cos theta. So the dot product formula When I replace the magnitude of the projection with what I know it's equal to, it looks like this. Magnitude of vector b times magnitude of vector a times cosine of the angle between them. So the first thing we're going to fill out, we're going to write down what the magnitude of the projection of a onto b is equal to. It's equal to the magnitude of a cos theta, and we figured that out using our diagram. So the magnitude of the projection of a onto b equals the magnitude of a times cosine theta. There's only a slight problem with this though, because this only works for when the angle is between 0 and 90. If the angle is between 90 and 180, the cosine ratio is actually going to be negative, and when we're finding a magnitude of a vector, we don't want to include a negative, so we can get rid of it just by multiplying this product by -1. So -1 times the magnitude of vector a times cosine of the angle. So that's how we would find the magnitude of the projection if the angle is between 90 and 180. So now we know how to find the magnitude of the vector projection if we're given two geometric vectors. Now I can come up with the vector projection formulas. Since I know the magnitude of the vector projection, I now just have to give a direction to it. I just have to give a direction to this. So I know the magnitude of the projection, just give it a direction. Well, what direction do projection vectors go in? If I'm projecting vector A onto vector B, notice it's going in the same direction as vector B. It's parallel to vector B. So all I have to do here, if I want a formula for the projection of A onto B, so this is the vector projection, notice there's no magnitude symbol here. So the projection of A onto B, I know its magnitude is the magnitude of A times cosine theta. And what direction is it going in? It's going in the direction of B. But I don't want to change its magnitude, so I can't multiply it by vector B, I multiply it by unit vector B. That looks like this. Here's the symbol for unit vector B, B with a hat above it. So I multiply the magnitude of it by unit vector B. That makes it go in the same direction as B. Or it might actually make it go in the opposite direction if the angle was between 90 and 180. So I don't have to worry about two separate versions of it for this one, because the cosine ratio will take care of if it's going in the same or opposite direction as vector B. Remember unit vector? I could also rewrite that as vector B divided by its magnitude. That's what unit vector B is. That makes it go in the exact same direction as B, but have a magnitude of 1. So either version of this is fine for finding the vector projection of A onto B. So let's see what this looks like in an application question. So let's do a couple applications of vector projections for geometric vectors. So part A, I have two geometric vectors here. It says determine the projection of U onto V. If I want the projection of U onto V, we can use the formula we came up with, projection of vector U onto vector V. So I should also give you a diagram of what this would look like. So I've just extended an imaginary line going in the same direction as vector V, and the projection, its tail is going to be at the same place as the tail is U and V. It's going to be parallel to V, and the tip is going to go to a point where if I were to connect it to the tip of vector U, there would be a 90-degree angle with the projection vector. So my projection vector U onto V is indicated with this green vector here. So what's the formula for calculating it? The projection of U onto V equals the magnitude of U cos theta, but I need to send that in the same direction as vector V, so I need to multiply this by unit vector V. By multiplying it by the unit vector V, that makes sure to not change its magnitude, it just gives it a direction. So this would equal the magnitude of U is 5, cosine of the angle between the vectors is 50, and multiply that by unit vector V. And now I can get an approximate value for 5 cos 50. It's about 3.21. So since this is positive, I know it's going to be going in the exact same direction as V, and its length is 3.21. So I have a vector that's going in the exact same direction as vector V, and its length, if I were to calculate its length, it was 3.21. Part B, same type of question, but this time we have an obtuse angle. So I just want you to make sure that you understand how this formula works. So if I want the projection of P onto Q, that would equal the magnitude of P cos theta multiplied by unit vector Q. Also, let me draw a diagram of what it would look like. So I just extended that imaginary line parallel to vector Q. And here would be the projection vector. I know it's going to be parallel to vector Q. tail at the same spot, and tip stops at a point so that if I were to connect it up to vector P, it would form a 90-degree angle. So this green vector is my projection vector. This part of the formula gives me its magnitude. This gives me its direction. So when I use this formula, the magnitude of P is 20. Cosine of the angle between them is 120. Multiply that by unit vector Q. When we do cos of 120, that's actually equal to negative a half. So I have 20 times negative a half times unit vector Q. So that gives me negative 10 unit vector Q. So let me make sure you can interpret this answer properly. Remember, unit vector Q means exact same direction as Q, but with a magnitude of 1. When I multiply that unit vector Q by a negative, it then sends it in the opposite direction. So I'm now going in the opposite direction of vector Q. Vector Q is going this way, and my projection vector is going the opposite direction, that way. And that's indicated by this negative right here. And what's the magnitude of that vector? It's 10. So to sum it up, my projection vector has a magnitude of 10, and it's going in the opposite direction of vector Q. Part C actually gives us algebraic vectors. We know the x and y components of the vectors, so we're going to have to go back and come up with the formula for the algebraic vectors if we want the magnitude of the projection or the vector projection. Let's look down here at this formula for dot product before I replace the magnitude of the projection with magnitude A cos theta. Let's just look at this version of it, and let's isolate the magnitude of the projection. So the magnitude of the projection of vector A onto vector B equals the dot product divided by the magnitude of B. So A dot B divided by the magnitude of vector B. So if I want the magnitude of the projection, if I'm given algebraic vectors, I could calculate its dot product and the magnitude of one of the vectors. So I could use this formula to find the magnitude of the projection of A onto B if I had algebraic vectors. So the magnitude of the projection of vector A onto vector B is equal to A dot B over the magnitude of B. And remember, the dot product is positive if the angle is between 0 and 90, but negative if the angle is between 90 and 180. So just like over here where we needed two versions of the formula, over here, since I only want the magnitude of the projection, I don't want a negative value, I would want to make sure I always get a positive answer. So two options. We could break it into two formulas like we did over here, and when the angle is between 90 and 180, we multiply it by negative 1. Or I could just throw some absolute value symbols around this, telling me that I only want the positive version of this. I could have done that over here as well. I could have just thrown some absolute value symbols around that, and then not worried about having to do two different versions of the formula. But I wanted to make sure I reminded you that between 0 and 90, cosine is positive, which means the dot product is going to be positive. And between 90 and 180, cosine is negative, which means the dot product would be negative. So I wanted to take the time to remind you about that. That's why I did two versions of the formula there. But over here, let's just do one version of the formula, just put some absolute value symbols around it. Now if I want the vector projection of A onto B, I just need to give this part of the formula a direction. So the projection of A onto B equals A dot B over the magnitude of B. But now I have to multiply this by the direction that it's going in. Well, what direction can a vector projection go in? If we're projecting A onto B, we know that it's going to be parallel to B. It's either going to be going in the same direction as B if the dot product is positive, or it's going to be going in the opposite direction of B if the dot product is negative. Right? Same direction if we're between 0 and 90, opposite direction if we're between 90 and 180 for the angle between the vectors. So by multiplying this by unit vector B, I accomplish that. Unit vector B, remember, is a vector that's in the same direction as B but with a magnitude of 1. So if I take that vector and multiply it by this magnitude, it either takes it in the same direction as B with this magnitude if the dot product is positive, or if the dot product is negative, this unit vector gets multiplied by a negative, which sends it in the opposite direction of B. So it takes care of both scenarios that we want. So this is the formula for the vector projection of A onto B. And remember, we could actually calculate unit vector B by doing vector B itself divided by its own magnitude. That gives us a vector in the same direction as B, but with a magnitude of 1. And I could even simplify this formula. Let me give you another version of this formula. So I'm going to simplify this by multiplying the numerators and denominators. Well, look in the denominator. I have magnitude of b times magnitude of b. That's the magnitude of b squared, which actually is equal to b dot b. And I'll prove that to you in just a second. But the magnitude of b squared is equal to b dot b. And in the numerator, I've got a dot b times vector b. So I'm just going to put the a dot b here, and I'm going to write the vector b off to the side here. So make sure you have all of these formulas filled out very carefully, because we're now going to be solving some questions that ask us to find vector projections or magnitude of vector projections for either geometric or Cartesian vectors. And also, before we do that, I said I would prove to you that the magnitude of b squared was equal to b dot b. So I'll do that quickly now before we do some examples. So let me remind you that the magnitude of b would be equal to the square root of the x component squared plus the y component squared. So what's the magnitude of b squared equal to? Well, if I square both sides, this square root is gone. So the magnitude of b squared equals this. And what does b dot b look like? If I did b dot b, that would be the product of the x components of both. So the x component of b times the x component of b plus the y component of b times the y component of b. That's just x component squared plus y component squared, which is exactly what this is. So part C, I wanted to determine the projection of D onto C. So 2, negative 3, so this is vector D. And C is 1, 4, so this is vector C. I want to figure out the projection, so it must mean the vector projection because it doesn't have the word magnitude, of D onto C. So if I'm projecting D onto C, since the angle is bigger than 90, I know it's going to be going in the opposite direction of C. So it's going to look like, let me do it in green, it's going to look like this. This is going to be my projection vector. It's going to form a 90-degree angle there. So the projection of vector D onto vector C would equal, if we use the formula we came up with, it would equal D dot C over C dot C times vector C. So let's calculate all of this. D dot C would be 2 times 1 plus negative 3 times 4. I'm just finding the product of the x components and adding the product of the y components over c dot c. So that would just be 1 times 1 plus 4 times 4. So that's 1 squared plus 4 squared. And this needs to be multiplied by vector c. So multiply it by the vector 1, 4. So this equals 2 plus negative 12. That's negative 10 over 1 plus 16. That's 17. And then I could distribute this scalar into this vector, or I could leave it in the form it is there. I'll distribute it in. So this would be the vector negative 10 over 17, comma, negative 40 over 17. When you multiply a vector by a scalar, you can think of it as distributive properties. Multiply the x component by the scalar and the y component by the scalar. And this would be what this vector projection would look like. So this is the vector projection of D on C written in algebraic form. For part D, we're interested in finding the magnitude of the projection of vector A onto vector B, and they're given to us as algebraic vectors. So we can use the formula we created earlier and that we wrote on the formula section of this lesson that told us that the magnitude of the projection of vector A onto vector B is equal to A dot B divided by the magnitude of vector B. And we want the absolute value of this since we want the magnitude. And the dot product could be negative, so we decided that we would put absolute value symbols around there to show that we want the positive value of this. So let's start by finding the dot product of vector A and B. So multiply the x components plus multiply the y components. 4 times 4 plus 3 times negative 1. And this needs to be divided by the magnitude of vector B. And to find the magnitude of a vector, you do the square root of the sum of the squares of its x and y components. So for vector B, the x component is 4, so I would have to do 4 squared, plus the y component squared, so negative 1 squared. And I want the absolute value of this. In the numerator, I have 16 minus 3, that's 13. And in the denominator, I have the square root of 16 plus 1, that's 17. So this is already positive, so I don't have to worry about the absolute value symbols. So this is the magnitude of the projection vector A onto B. That's the length of it. Part E asks us to find the vector projection of A onto B. So I know from part D, I know what its magnitude is. But what I want to know now is what is the vector projection. So I also need to include the direction that goes with it. So there are two ways we could do this. And let me start by just drawing what we're trying to figure out here. So we're now trying to figure out the actual vector that is the projection of A onto B. So I know what that vector would look like. So this is what the vector projection looks like of vector A onto vector B, this green vector right here. I'll label it the projection of vector A onto vector B. And if I want to write this as an algebraic vector, I can use the formula we came up with on the formula page. The projection of vector A onto vector B is equal to A dot B divided by B dot B multiplied by vector B. And now I can just evaluate this, since I have the algebraic vectors A and B. A dot B, find the product of the x components, 4 times 4, plus find the product of the y components, 3 and negative 1. I know we already did this in part D, but we're just doing it again. And B dot B, well, I'd have to multiply the x component of B with the x component of B, so 4 times 4, which is 4 squared, plus the y component of B with the y component of B, so negative 1 times negative 1, which is negative 1 squared. And this needs to be multiplied by vector B, which is the vector for negative 1. And I've written that in square brackets because that is a vector, so make sure you write that in square brackets. And now if we evaluate this, 16 minus 3 is 13. And in the denominator, I have 16 plus 1, that's 17. And that is being multiplied by the vector for negative 1. And then I can multiply the x and y components of the vector by the scalar. Imagine distributing that scalar to both the x and y components. So 13 over 17 times 4 is 52 over 17. That's the x component of my projection vector. And the y component, 13 over 17 times negative 1, is negative 13 over 17. So here are the approximate values of the x and y components from that vector. Remember, when you have a vector written in algebraic form like this, the x component of that vector tells you the x coordinate of where the tip would be, and the y component tells you the y coordinate of where the tip would be if the vector was translated so that its tail is at the origin, and that's where it is. So I know that the tip, the x coordinate is about 3.1, and the y coordinate is about negative 0.8. So notice that is the vector that we found there. It matches up with the answer we got algebraically. So I had mentioned we could also do this question another way. Since I already knew the magnitude from part D, I already knew the length of the projection vector, I could get the vector projection by just giving it a direction. And I know the direction of the projection vector A onto B is going to be parallel to vector B. So all I would have to do is take its magnitude, 13 over root 17, and give it a direction. But I need to make sure I don't change that magnitude, so multiply it by unit vector B. Unit vector B has a magnitude of 1 in the direction of vector B. And unit vector B, we could calculate that by doing vector B, which is 4, negative 1, divided by its own magnitude, which we've already calculated is root 17. And then we just have to simplify this. In the denominator, I have root 17 times root 17, that's just 17, and that's being multiplied by the vector 4, negative 1. That's exactly what we had over here, so you can see that we would get the same answer doing it this way. But if you feel more comfortable just starting from the beginning, then this formula was perfectly fine. It did the same thing. But since we already had the magnitude from part D, we could have just multiplied that magnitude by unit vector B and gotten the vector projection. Example 4 says a shoe store sold 350 Nike shoes, 275 Adidas shoes, and the price for Nike shoes is $175 a pair, and the price for Adidas shoes is $250 a pair. And I should mention those are the pairs that they sold in a year. It says write a Cartesian vector, vector S, to represent the number of pairs of shoes sold. Okay, well, the Nike company sold 350, and the Adidas company sold 275. So you may be thinking, okay, well, why are we writing this like a vector? Well, you'll see how it all works out in just a minute. Part B says write a Cartesian vector, vector P, to represent the prices of the shoes. Since when I did my number of shoes sold, I did Nike first and then Adidas second, I should follow the same pattern when writing the price vector. The Nike shoes were 175, the Adidas shoes were 250. So the price vector would be 175, comma, 250. Part C says find the dot product, S dot P. So S dot P would equal, I would need to multiply the x components So 350 times 175, plus multiply the y components. So 275 times 250. And now I can just evaluate this product, and I get 130,000. And what does this answer represent? Well, if we look at the products we found, this product has to do with the Nike shoes. They were both the X components which I made the Nikes. This was the number of Nikes sold, and this was the price that each of them cost. And this product was for the Adidas shoes. This was how many Adidas shoes that were sold, and this was the price of them. So when I do number sold times price, I get my revenue. So this number down here is the combined revenue between the sales of the Nike and the Adidas shoes. It was a revenue of $130,000. So that's what that answer represents. So that's the end of the lesson. There were a lot of formulas that we worked with vector projections. So we came up with a lot of formulas for vector projections that you're going to have to practice. So make sure you go ahead, go to jensenmath.ca, get the practice problems, and practice working with those projection formulas. And hopefully you understand where they all came from. So that's it.